Yeah, thanks for the invitation, and really excited to share some of the work our team's been doing. So just to begin with, why is partial reprogramming exciting? And it's because fundamental unit of the body is the cell, and where is aging coming from? It's coming from every cell in your body. So if we can get to the bottom of aging in a cell, and we can cut across the body to get to all of your cells, we might do something quite dramatic to lifespan. So that's the idea. Seems to be a point of leverage. Obviously, we need to prove that, but that's sort of behind the excitement. Oh, I've broken the presentation, sorry. Thank you. Okay.
Oh, down. It is a PDF. Oh.
Okay, so I'm going to switch the title up a bit. So, firstly, talk about the realities, and then I'm going to talk about the potential. So, realities is a sort of summary of what is known, at least what is known in my head, and sort of more broadly in my team.
If you prefer to use that, you don't have to. You can walk around.
Oh, thank you. Yeah. Testing. Yeah. So, Yamanaka, a Japanese scientist who in the mid-2000s discovered how to turn somatic cells, like your skin cells, into stem cells. And what he didn't realise at the time is that the biological age of those stem cells at the end of this process was 0. So he'd actually reversed age. And so, looking at these stem cells, they were remarkable. They behaved like embryonic stem cells. And, embryonic stem cells do have an age of 0. So there was a little bit of evidence this had happened, but it wasn't until a little bit later that there was a more definitive result. So Steve Horvath in 2013 discovered the multi-tissue DNA methylation clock, so very robust biomarker of age, highly correlated with age in single tissues, works across multiple tissues. I could talk a long time about clocks, so I won't for this presentation. But Tamir Chandra at University of Edinburgh basically took Yamanaka's data and applied the clock algorithm to the methylation data. So this blue line is the methylation age of 62-year-old fibroblasts over a period of expression of about 50 days of Yamanaka pattern. So you can see between 0 and 20 days, the clock reversing from 62 years all the way down to 0. Which at the time was an astonishing result. Like slowing down aging or stopping aging was exciting enough, let alone reverse aging. So at the time this result was published, I just disproved the hypothesis behind my company Shift. I was looking at mitochondrial DNA damage. The clock was not responding to this damage, even though we had a therapeutic approach. Simultaneously, Tamir Chandra showed that not only could you do something about the clock, you could reverse it. So it was quite clear at that point there was something really exciting going on under the bonnet of Yamanaka factors. So why not use Yamanaka factors all across the body? Let's see what this does to lifespan. Why try any harder? And the reason is obvious in hindsight. It's because these factors were always designed to make stem cells. That's what Yamanaka was optimizing. How do I turn an adult cell into a stem cell? So that was the feature he was optimizing. The bug was rejuvenation. So you've got to remember, these are pluripotency inducing factors. That's what they were designed for. And one of the qualifying assays of a pluripotency factor is when you express it in an animal, it creates a multi-tissue tumor called a teratomas. This slightly grisly picture at the bottom is 2 arrows pointing to 2 growths that shouldn't be inside the body cavity of that mouse. So I think the bottom line is this is incredibly exciting that you can reverse the age of cells, but clearly there's a lot we don't know, specifically everything about rejuvenation apart from the Yamanaka factors. That's all we know at the moment. There's these 4 factors, never designed for rejuvenation, but aren't we lucky that we happen to encounter cell rejuvenation in the first place? So this reversal in cellular age, does it mean anything beyond the clocks? Does it mean anything beyond hallmarks of aging, which are also reversed? And the answer is yes. So in 2016, a scientist, I think, sort of on the West Coast to begin with, called Giancarlo Belmonte. He showed that in a progeroid mouse, so this is a mouse where you mutate a nuclear laminin to create a protein called progerin, where those mice basically show accelerated aging. Even in the presence of that mutation, if you overexpress Yamanaka factors, you can increase the lifespan substantially. So remember, the mutation's still there, and then you're using Yamanaka factors, which don't seem to have any direct link to the mechanism of action of this model. So you overexpress the factors and you increase lifespan. So I think synthetic rescue might be the appropriate term. And it wasn't until much later that this result was reproduced in just physiologically aged mice, so not special progeroid mice that age faster, but just mice, black 6J mice that have lived 2 years. And I think it was Rejuvenate by, it's actually a commercial initiative, not scientists, or scientists within a commercial initiative. He overexpressed OSK, so this is 3 out of the 4 factors, but minus the oncogene c-Myc. Those 3 factors were put into an adenovirus with quite a broad tropism, meaning it can go across lots of the body, the idea being you can try and rejuvenate lots of cells, and that would have greater impact on lifespan. And they were able to double remaining lifespan according to the median lifespan. So this was a result that was conspicuous by its absence for quite some time, but that result finally came in, I think it's two or three years ago now. So these factors can have an impact on lifespan. There are other interventions that impact lifespan more significantly, but this does show you there's a proof of concept. Like if we reverse cellular age, we can also impact lifespan. And then for any reprogramming aficionados, these are some of the latest studies. So this is, again, a publication by Giancarlo Belmonte. It's what characterises a new hallmark of aging, which is the identity of most of the cells across your body seems to drift towards fibroblast identity, specifically activated fibroblast identity as you get older. So it's quite an interesting phenomenon, like this loss of self, at least at the cellular level. And he shows that partial reprogramming pulls that back. So you've got this new hallmark of aging. He hasn't called it a hallmark, but for the sake of argument, there's this new hallmark of aging. And reprogramming is reversing that as well. So I talked about the clock, but here's a new feature, and that's reversed. David Sinclair, in collaboration with Jonathan Weissman, he's one of the scientists behind single-cell omic technology, so I take this quite seriously. He characterises a downstream pathway of the Yamanaka factors, which is a sort of resilience pathway, and basically shows that reprogramming is activating this resilience pathway, and that might have something to do with benefits in vision loss, which is one of these early applications for the factors. So that's some of the latest papers. So moving on to the potential of partial reprogramming. So to begin with, I just want to describe the technologies we use to find some new rejuvenation genes. I won't be able to discuss this in a lot of detail today. It'll be a much longer talk. So I'll just discuss those at a high level, but I will then move on to the findings, which sort of they make the tools more credible, the fact we actually found something in the first place. Otherwise, there'd just be some interesting tools. But they did actually come together and do something useful. So there's two tools, and these are both products of machine learning that I want to discuss. So one is a single cell aging clock. So you might have heard of epigenetic aging clocks. This is a way to robustly measure biological age, but at a bulk level in like a whole petri dish of cells. You can't look at the single cell level at what's going on with aging. One of the things I spend a lot of time with my team doing is building a big data set of lots of different fibroblasts of different ages, collecting the methylome, collecting the single cell transcriptome, and with machine learning, finding a way to predict methylation age at a single cell level from the transcriptome. So we have like a proxy of the methylation clock within gene expression. So that's tool number one. That's a product of machine learning, a single cell aging clock. The second tool is actually sort of blows my mind this exists, but it does exist. So we call it a virtual cell. There's other labels for this. I think cell perturbation model, cell simulation. But just describe where this thing comes from. So if you take a machine learning model like a transformer or a graph neural net, and you feed it single cell data, so single cell transcriptome data from tens of millions of cells, it learns the relationships between the genes. By looking at enough cells, it can establish if gene A is up, gene B is down. If gene C is up, gene A and Z are down. Right? It can look at enough cells, and now it understands how genes impact each other. And you can put that in a computer, and in silico, you can say, I want to overexpress 2 genes. What's the impact on the rest of the genes? And when you have a single cell aging clock, you can convert that gene signature into an age. So you're able to do these vast campaigns of experiments. So this on the right-hand side is a campaign of virtual experiments. It's about 350,000 experiments. Would have taken 5 years to complete in the wet lab, even with a single cell clock. It's about 1 week of compute. So you can see the power of having these sort of virtual cells. You can basically do every experiment you ever want to do and take the most exciting results, effectively from the future, right? You're sort of reaching into the future, picking out the best result, and that's what you get to test. So I think my favourite line is you can compress 3 centuries of future experiments into less than 1 year of compute. So it's like getting into the DeLorean, going to the 2300s, writing down the gene combination, bringing it back home, testing it, and those are the interventions we're testing at the moment. So for the Hawkeye view, we have change in age of virtual cell along the bottom. So what was, when we overexpress different combinations of genes, what impact does that have at the age of the virtual cell? So you actually see this peak at 2.5 years, which is an artifactual shift to the right-hand side because we electrocute the cells in the training data. So we think this is a feature of acute electrocution, so don't put your finger in the socket. You'll be 2.5 years older. But it's an odd distribution on each side of that. So in the green box are pairs of genes that rejuvenate the virtual cell. In the red box, there are pairs of genes that age the virtual cell, both of which are interesting from an intervention perspective. We might want to overexpress a rejuvenation gene, or combination of genes, or we might want to inhibit pro-aging genes. That might be good for us as well. And clearly, inhibition is much easier to do as a drug. Right? Most drugs are inhibitors. And there's just more options in terms of getting to the whole body. So is this useful, right? That's the question. Is it useful? And yeah, the answer is yes. And the great irony of having a virtual cell and a single cell aging clock is that the whole reason we built those tools was to explore combinatorial space. We thought we'd have to explore all combinations of 2 genes, 3 genes, 4 genes, because the Yamanaka factors are 4 genes overexpressed together. That's what we know. So if we're trying to find something better, let's stick with what works. And the first thing the virtual cell told us were there were single gene drivers across different combinations. So the same gene would feature across different combinations of genes that rejuvenate the virtual cell. And this gene, initially this was a speculative experiment. We said, let's take this gene, call it SP000, that's a code name. And on its own, so this graph in the middle is the change in epigenetic age. Now, these are real cells now in the dish using epigenetic clocks. I'm just showing you the most robust clock that we use, called the principal component skin and blood clock, from Steve Orvath and Ken Raj with Morgan Levine, doing a principal component transformation on the top of it. Again, I could talk about clocks a long time, but this is the most robust one that we rely upon. And you can see that GFP, we have no change in age over the duration of the experiment, which was 6 weeks, so this is constitutive expression over 6 weeks. OSK, this is in a bulk population, not in a sorted population. We rejuvenate 2.5 years in a single gene SP000, we're rejuvenating 5 years, so it's roughly double the velocity of rejuvenation. On your right-hand side, this was a key result for us, which is we're trying to find safer rejuvenation. So Yamanaka factors, they have this pluripotency inducing feature, right? That was their feature. Can we get away from that dangerous activity? And the answer is yes. It doesn't come out very well on this screen, but you have 4 panels. You see OSK and OSKM. You see this white dotted line. That's the boundary between the fibroblasts on the outside and a colony of induced pluripotent stem cells growing outwards. So you see with OSK, after 42 days, you do see colonies growing. OSKM, you see lots of colonies, as expected, but SP000, control, you don't see the colonies. So we were very excited to identify a single gene sufficient to reverse the epigenetic clocks. It's not reversing aging, right? That comes later, but at least this is our screening system. Reverse those clocks and not induce pluripotency. So the next question for us was, can we rejuvenate different cell types? Because these are just fibroblasts. And ultimately, we want to rejuvenate as many cell types as possible, get across your body, and see what happens after that. And there is a lot of good news in this presentation. It's not all good news though. I'm showing you 2 cell types, each with 4 different epigenetic clocks, just to show you how robust this single gene is. So we've got principal component skin and blood, principal component multi-tissue, geodenpase age, and GRIM-H2. And you see GFP, OSK, SV000. And you can just see like robustly we're rejuvenating across those different clocks. In keratinocytes, we're also robustly rejuvenating across those clocks, but at a much higher velocity. It's very interesting. This whole discovery system was built for fibroblasts. When we try it in a different cell type, we were worried about not rejuvenating that cell type. We actually see more rejuvenation in the keratinocytes, surprisingly, and that seems to be more robust than OSK and the keratinocytes. In 2 of the clocks, you're seeing a sort of abnormal result with OSK. We don't have an explanation for that. And at this point, we've discovered 190 genes that impact our single cell aging clock. So 40 in the pro-aging direction, 150 in the rejuvenation direction. Clearly, some of them are more significant than others. And SV000 is sort of highlighted on this UMAP plot. So this is basically a way to represent single cell data. Each dot is a single cell. If the dots are close together, that means the gene expression is similar. If they're far apart, that gene expression is different. The colour of the dot is how the age of the cell changed during the experiment. So it's very blue, it got younger. If it's very red, it got older. So in total, we found 190 interventions. We ran a poll internally about how many do you think we'll find. And some crazy guy at 150. He wasn't crazy enough. It's great when that happens. It's so hard to get anything to work in biology. But when this came in, this was sort of a moment of celebration. We found at this point around 30 genes that reverse epigenetic clocks significantly, 10 of which outperform OSK. So you see this red dotted line is OSK, and 10 genes that individually are sufficient to rejuvenate in excess of OSK. So it looks like rejuvenation is more distributed than we expected, and it's not just exclusive to Yamanaka factors. It seems to be, we don't know what the mechanism is, right, but it seems to be more distributed than we expected to begin with. Okay, let me get back to the right slide. And yes, I'm just going to go back here. So I've highlighted 2 genes. One is SV000, but one is a pro-aging gene called SV101, which originally we overlooked because we're not interested in making people older. But I sort of talked about maybe we might want to inhibit pro-aging genes because that's more druggable, right? We're more likely to develop something like a small molecule that can go across your body and impact that type of gene. So this gene is very special because SV101 is widely expressed across the whole body. So this is exciting because if we could do something with this gene, we could impact it across the body. It's only expressed in a few cell types. We can only impact it in those cell types, but this gene is expressed across the body. And more than that, it's actually been used outside of shift to impact lifespan and reverse fibrosis. So this was the first time the data took us to a specific disease target. It's sort of a big question for a company. How do you birth this new type of therapeutic through a disease-focused regulatory path? So this gene took us to fibrosis. And so we brought this intervention into our own systems, and we tried to inhibit this gene now. Because when you overexpress it, it ages the cell, but is it reciprocal? If we knock it down, can we rejuvenate? And the answer is yes. So we were able to get about 1 year rejuvenation per month velocity by siRNA knockdown of this gene. So it's roughly a third of the velocity of SV000 when you overexpress it. So there does seem to be some compromise. And more than this, you can, this is an 8-week experiment, so 2 years across 2 months. And we're also able to prevent fibrosis, so we pre-treat cells with an siRNA, and then we induce fibrosis with TGF-beta. This siRNA completely prevents fibrosis when we get on with it. We just intercepted some external data where some investigators completely, for other reasons, looking at SV101 siRNA in fibrosis, showed you can reverse MASH in a rodent model. So I've recreated the data, otherwise you can trace it back to the author, and my company's out of business. But it's incredible. So these investigators went into a mouse, they reversed fibrosis. Little do they know, this is actually a rejuvenative gene. So I guess that's the difference between when we're looking at this and say when this investigators are looking at it. So this gives us this development path. We were looking for this mouse data. We were actually funding to do the mouse data, and then it's like a gift from the universe, right? Somebody's done it for other reasons. And so we're a little bit on the back foot. It's like, well, now what, right? With that, so we're going to sort of mix up what we're doing in the next few months. You can also impact this gene target by small molecule. So there's a binding partner that has a nice pocket, and there are molecules that can interrupt the binding of that partner to SV101, and you can rejuvenate slightly less than the siRNA and prevent fibrosis. Unfortunately, this molecule is toxic to the second cell type, so it's not ready for prime time, but it does show you small molecules are within the realm of the possible, which is exciting, right? Because the molecule can get across your body. I've got to go fast. There are multiple family members in this SP000 family. Some of these family members, all of which have very similar protein sequence. Many are rejuvenative. One is not rejuvenative. So it's this pink arrow at the bottom. It's very similar protein sequences, very different levels of rejuvenation. So we've identified the sequence specific to the rejuvenative family members, absent in the non-rejuvenative family members. And we're co-folding every other protein in the genome to that sequence using like an AlphaFold type algorithm. And we're actually finding a bunch of candidates that we're about to test. I think I'll be shut down. Okay, just some feel-good stuff at the end. Next year for us is Year of the Mouse, so we want to rejuvenate the liver, want to impact fibrosis, although that's happened externally. We want to go into hearing loss. There's lots of evidence that will be useful with rejuvenation gene, and then we want to impact lifespan. Like see, we're outperforming in these early assays. What can we do in a lifespan setting? And I just wanted to, we're going to make these special mice that they're born with the gene inside their body, and the purpose is, if we express this gene across the body, is it safe? Because if we develop the molecule and it wasn't safe to get across the body, that would be a tragic way to find out. Right? It's better to say, prove the safety of this gene immediately, then there's a reason to develop the molecule and get across the body with a drug. So just some notes on the guiding mission. So enrich these gene targets with systemic efficacy and safety, right? So we can get across the whole body. Link those to the most systemic compatible drug modality, so we've got maximum effect size, and then gain maximum traction on lifespan. And I wanted to end on the feel good. So, ultimately, we want to make this a mundane scenario where it's like the obvious thing to do. These pharmaceuticals exist. Why wouldn't you take them and keep yourself in good shape? It's socially irresponsible to do so. Your loved ones would be telling you to do this. What are you doing? Not taking your medicine. So this is sort of on the later path, but this is something very exciting. It's one of the reasons we do this. We get up every day, and also I want that amount of energy, and I want to see these things happen, and I want to be able to get into orbit. And you're going to need really good biology to do that. It's a rough ride getting into space and coming back, let alone being old. Right? It can actually do some terrible things. So I think these types of technologies give us the ability to do very new things. We shouldn't forget that and how exciting this is. So I just wanted to end on that.
Thank you so much, Dan. Wait a minute, you might have a couple of questions.
Yeah, sorry.
One quick thing I was going to say is that your transgenic expressor, don't be put off if you do see something. Pharmacology is all about dose. So there are lots of things we expect, particularly, is it conditional, the transgenic? Will you be able to switch it on?
Yes, it'll be an inducible. Yeah, inducible.
Yeah. Well, that's exciting. The questions, Daniel. Mind's blown again. It's amazing data. Come on, what's your question? No?
I'm going to get them later.
Going to get them later.
Can we ask one quickly?
Dr. Penny's going to get you later.
Thank you for that. It's obviously really interesting to see stuff getting down the line, preclinical, maybe clinical at some point. I understand the protecting the commercial interests. I'm curious if there is already research out there, maybe not looking directly at this gene target for rejuvenation purposes, but why haven't you filed for some kind of intellectual property protection, and then you can say what the gene target is in some way, just to give a bit more scientific validation to what you are doing.
So, yeah.
Yeah, I'll speak loudly. So yeah, we do try to cover our footsteps so we can share as much as possible. So we do have IP on that, but there are certain sort of metadata around that where someone can. There's lots of loopholes people can get around things. So I guess it's in our interest to obfuscate for the foreseeable future. But I can give you some detail. So this gene SP000, very conserved, almost perfectly conserved in mammals. Also highly conserved all the way to worms. So that's interesting. It flashes in and out. Well, very rarely expressed across the body, with the exception of the germline in early development. So it flashes on and off in the germline in early development. So we don't know what that means, but maybe it's something to do with this natural rejuvenation event. Like we can't prove this is causation. It might just be correlation. So yeah, there's some interesting features like the conservation and the fact it's sort of expressed specifically in part of the body which is responsible for resetting age for the next generation.
Brilliant, thank you. Thanks very much.